In this section, we want to look at what are called polar coordinates, and polar coordinates are just another way to name points in the coordinate plane. So I've written this diagram over here, which is our standard diagram for trigonometric functions, the definition that we've had right from chapter 1. But I can name this point right here with coordinates x and y, or I can name it with these coordinates r and theta, where I give the address of this point as being a distance r out on a ray that's theta degrees from the positive x-axis measured, in a counterclockwise direction like we do, or theta is an angle in standard position. So this point right here has rectangular coordinates x and y and polar coordinates r and theta. So the relationship, of course, is sine theta is y over r, which means that y is r sine theta. Cosine theta is x over r, which means that x is r cosine theta. So if I was given r and theta and I wanted to find x and y, I would simply substitute into this formula right here. The other relationship is that r squared is equal to x squared plus y squared by the Pythagorean theorem, and I can use this and these right here to go back from coordinates x and y to coordinates r and theta. So in this first section, what we want to do is just simply get used to polar coordinates, graph some polar coordinates, and then change back and forth between polar and rectangular coordinates. So let's look at our first example. We want to graph these points that are in polar coordinates, 3 and 150 degrees, 1 and negative 225 degrees, and negative 3 and 45 degrees. Now I've written a coordinate system, drawn a coordinate system over here, which is a polar coordinate system. These circles are at 1 unit, 2 units, 3 units, 4 units from the origin. So each 2 lines right here is 1 unit, the way I've drawn this. So to graph the ordered pair 3, 150 degrees, I go from the positive x-axis to the ray that's at 150 degrees out from the origin, and I move 3 units out on that ray. So from the origin, I move 1, 2, 3 units out on that ray. The coordinates of this point are r equal 3, theta equal 150 degrees. Now, my next point is 1, negative 225 degrees. So I start here at my positive x-axis, and I go back 225 degrees, and I go 1 unit out on that ray. So that is this ray right here that's at negative 225 degrees, and I want to just go 1 unit back out on it. So this is the point then, negative 1, negative 225 degrees. I won't write the coordinates there. Next, I want to go negative 3 units out on the ray that's 45 degrees in the positive x-axis, or the angle, the terminal side of the angle in standard position, 45 degrees. So here is 45 degrees right here, and I want to go negative 3 units out on that ray. So here's 45 degrees, and negative 3 units will be 1, 2, 3. So this is the point, r equal negative 3, theta equal 45 degrees. So my angle in standard position is 45 degrees, and if I want to go negative 3 units out on that, on the terminal side of that angle, I go back through the origin the other way 3 units. So I can have positive or negative values for r, and I can have positive or negative values for theta. Usually we like to try to keep theta between 0 and 360 degrees and r positive or negative if we can. But if theta is between 0 and 360 degrees, it's a little easier to name. However, we can use negative angles. There's no problem with that. Now, let's do the second problem that says, what other points name the point to 60 degrees? So I want to look at the point that's 2 units out on the terminal side of 60 degrees in standard position. So here's 60 degrees right here, and I want to go 1, 2 units out on that. So there's the point 2, 60 degrees. Well, what other ways can I name this same point that's out on this ray 60 degrees? 2 units out on the ray 60 degrees, 1, 2. Well, I can name it this way by naming my angle with a negative number. So that would be negative 300 degrees and 2 units out on that ray. So 2, negative 300 degrees. Or I could name it as being in the opposite direction on this ray right here, which I can say is 240 degrees, and then I'll go back 2 units on it. So I can come out to this angle whose terminal side looks like this, 240 degrees, and I'll go negative 1, 2 units out on that ray. Now another way to name the same point is with negative 2 and negative 120 degrees. So in polar coordinates, the coordinates of a point are not unique. There's an infinite number of ways actually to name each point in the coordinate plane with polar coordinates. We've just, for this point right here, 2 and 60 degrees, named it 4 ways with angles between negative 360 and positive 360. If I look at all the angles that are coterminal with 60, for instance, if I can go 360 plus 60, that's another angle that has this same terminal side, and I can go 2 units out on it. So you can see there's an infinite number of ways to name every point in the coordinate plane with polar coordinates. It's not the same as rectangular coordinates. Next, what we want to do is convert back and forth between polar coordinates and rectangular coordinates. Here's our first example. Convert to rectangular coordinates, and I have square root 2, negative 135 degrees. So this is, let's just draw a picture, first of all, that will tell us about what this looks like. Negative 135 degrees, okay, that's going to be back this way. There's the ray, negative 135 degrees, and I want to go square root 2 units out on that. So I'll just draw this point right here and call that square root 2. Well, if that's the case, then I could just, since this is square root 2, this is 90 degrees, I know that's going to be 1 and 1 because that's 45 degrees, the reference angle for negative 135. So if that's the case, this point that's at square root 2, negative 135 degrees in polar coordinates would have rectangular coordinates, negative 1, negative 1. Now let's see if we can do that with a formula rather than just the picture. So I have r equals square root 2, and I have theta equals negative 135 degrees. So from my formulas, I know that x is equal to r cosine theta and y is equal to r sine theta. So that's square root 2 cosine negative 135, and that's square root 2 sine negative 135. And I think you know that cosine and sine of negative 135 degrees are going to be negative 1 over square root 2. When I multiply by square root 2, I'm going to get negative 1 and negative 1 for my x and y coordinates. So if I have a point written in polar coordinates, switching to rectangular coordinates is really easy. I just substitute directly into these formulas right here, r cosine theta and r sine theta. I'll get the correct coordinates out, which are x equal negative 1, y equal negative 1, which is the same thing I can see by looking at my picture right here. Now, if you can't, in this case, I could draw the picture and just get the coordinates from the picture. It's not always that way, so I need to be able to use the formulas too. But you can see everything's consistent. The picture works and the formula works too. The next problem, I want to take rectangular coordinates and convert to polar coordinates. So I have negative 2 square root 3 and 2. Okay, let's, in this case, draw a little picture of this. This will be in quadrant number 2, negative 2 square root 3 and 2. This will be a little bit longer. So I'll go back, say, to this point and then up to right here. This will be the point negative 2 square root 3 and 2. So this line segment right here is 2 square root 3 units long, and this line segment right here is 2 units long. So I want to name this point in polar coordinates. Here's my angle theta, and this is my distance r. This is the reference angle for angle theta, which is theta with a little hat on it. Okay, so what can we say? Well, first of all, the r is equal to the square root of x squared plus y squared, so that's 2 square root 3 squared, which is 4 times 3 or 12, plus 2 squared is 4. That's the square root of 16, which is just 4. So I know that r is equal to 4. Then the sine of my reference angle, I'll just take the sine of the reference angle here, 2 divided by r, 2 over 4, which is 1/2. That implies that the reference angle is 30 degrees, and that implies that the angle itself in quadrant 2 with a reference angle of 30 degrees must be 150 degrees. So what do I have? I have r and I have theta, so the coordinates of that point in polar coordinates must be 4 and 150 degrees. So by drawing this little picture right here, I could find r very easily. It's the square root of x squared plus y squared. Then the sine of theta, the sine of the reference angle is y over r, or the opposite side over the hypotenuse in this diagram right here, and I get that. If I wanted to go directly to the formula, I would have to say sine theta is y over r, cosine theta is x over r, actually substitute these values in once I found r, and then without looking at the picture, based on what the two values of sine theta and cosine theta came out to be, I'd get the 150 degrees directly. But in any case, I think always draw this picture if you can. It will really help in going back and forth between polar coordinates and rectangular coordinates, and also in becoming more intuitive about polar coordinates. I want to do one last problem where we take an equation in polar coordinates and write it in rectangular coordinates. Let's take a look. R squared is 4 sine 2 theta. Okay, so I have 4 sine 2 theta. Now I'll just tell you a little trick here. I wait and convert r squared later. R squared is x squared plus y squared. Okay, so that's an easy conversion. But first I need to get everything in terms of sine and cosine of just theta, not 2 theta. So I'm going to write this as 4 times 2 sine theta cosine theta. So that's r squared is equal to 8. Sine theta is y over r. Cosine theta is x over r. So I make a conversion for my trig functions first, y over r and x over r. So that means that r squared is 8xy over r squared. Now I'll multiply both sides by r squared, and I get r squared squared equals 8xy. R squared is x squared plus y squared equals 8xy. So there is the rectangular coordinate version of this equation in polar coordinates. Now, as you can see, x squared plus y squared squared equal 8xy. That's not an equation that we have graphed in rectangular coordinates. I wouldn't even know where to begin to graph it. But as you'll see when we get to the next section, graphing these equations right here in polar coordinates turns out to be a pretty easy proposition compared with graphing these equations in rectangular coordinates. So there's some graphs that lend themselves to polar coordinates, and we will, in the next section, take a look at the graphs of things like this, and then occasionally maybe look and see if they correspond with something we know from rectangular coordinates. In any case, that's an introduction to polar coordinates.